So we are going to discuss a new example, actually a frame using the displacement method. So you can determine first, if you are going with displacement method, what is the kinematic indeterminacy, right? So kinematic indeterminacy means the number of available degrees of freedom at the joints. Now here it's a pin support, right? So you have only rotation. So you have 1 degree of freedom which is not restrained. Here you have rotation as well as the deformation in the other directions as well. Here also you can it right. So here no, it is 0. It's a fixed support, right? So here you have 3, here you have 3. So what actually happens is, so your kinematic indeterminacy is originally 7, but they consider only bending deformation, so that they assume this is axially rigid. So if this member is axially rigid, this vertical translation is nearly, it's gonna be 0, right? So this vertical translation is gonna be 0 because these members cannot elongate. Why? The elongation is negligible, axially rigid, right? So, and the horizontal translation as well, these members are axially rigid. So the horizontal translation is also 0. There's no elongation, right? As well as this frame cannot move because it is restrained. Either frame can move and as well as the members elongate. So both will not occur, right? So this displacement is also 0, 0. So you will be remaining with 1 here and 1 here. Because if you know this rotation, right, it is exactly opposite, exactly equal to the other rotations. Because this joint is rigid, right? So if it's going to rotate theta, but it's keep its shape, right? If it is theta, theta, and theta, right? So okay. So yes, now we are okay, and we can go ahead with so this is bit tricky problem, right? So we have a couple of, so here is our first redundant displacement coordinate. Here it's our second. So we are taking the rotations, right? Here the sigma m is 0, but at the joint, but the members are not equal, right? There might be some values, right? But the summation is 0, but here the member values are exactly opposite and equal, right? So that means to know these bending moments, I need to take this part as well. So I will take that is the bending moment. I need to find the, so I will find all the actions, not the reaction, not all the, I will find all the bending moments, right? So here it's 0 because it's a pin support, no need to find, actually finally it would be 0. So here it would be the second action, here will be third, here it's fourth, here is my fifth. Okay, I will take this as well, sixth, doesn't need because fifth is equal to sixth, here seventh, right? So these are my actions I need to find. right? So these are my redundant, right? So first I will, in the displacement method, I'm fixing every redundant displacement. Why? I need to make them zero. That's why. So if you fix this, it cannot rotate. Everything is going to be zero, right? Yeah. Please consider this is 2EI. Everything is EI, EI, EI. So I'm fixing everything. I'm fixing everything. Right. So you have W load here. Sorry about that. So here I would say simple W, okay, per unit length. Okay. So I would say W into simple W into L is equal to capital W. So that's easy to simplify, right? So the, yes, if you fix everything, right, these are separated. So this beam is separated, so you can take the fix and moment easily. So here, now what we need to do? We are working in the displacement method. So that means we need to consider the equilibrium of these joints. So that means the bending moments, right? So first, the bending moments at my redundant coordinates. 1, 2, 3. The total, right? The total bending moment. So I'm taking clockwise positive. Okay. And then my members, the member forces which I need to find. So this is 1, this is 2, this is 3. When I say redundant coordinate, that means the overall joint, right? Overall joint. So this is 4, that's 4. 1, 2, sorry. This is 3. This is 4. This is 5. This is 6. This is 7th, right? So I need to find what? I need to find the bending moments, right? So that is the force, right? The force matrix and the action matrix I need to find at each step. So the force matrix I can find because I'm going to find the displacement. Why? Because we are in displacement method. So here, if you find this, so the fixed moment will be WL over. So this is L. This is also L. This is also L. And this is 3L over 2. Right? So this is WL over 8, right? And that would be anticlockwise. Is it capital W, L or simple? Yes, capital L. Right? Sorry about that. Right? So F1 would be So this would be W L over 8. Right. So at the second coordinate, you have fixed moment this only. Here it's 0, here it's 0, right? But it is anti-clockwise, right? So it's negative. Sorry, this is negative. Anti-clockwise, this is positive. WL over 8. Here you have, here it's 0. Here you will have an anti-clockwise bending moment. That's simple WL squared over 2L. Right? You can take simple W and L and substitute capital W and write and minus 12. Okay. So the first step was done, forces okay. So I need to find the actions. So my actions are, here it's 1, here it's 2. So for the forces, we consider each joint, right? Each joint. So the overall bending moment here, okay? Here the overall bending moment, but here separately. 1, 2, 3, 4, 5, 6, 7, right? So I need to find action restraint. That's going to be, first thing is, it is WL of 8. Second is 0, no loading. Third is 0. Fourth is 0. Fifth is 0. Sixth is WL over 12 minus. We substitute simple W into L as capital W. So watch the earlier videos on displacement method so you will understand the basics. So this is bit intermediate, okay? So this is done and this is done, right? So our force displacement method equation is actually what? Force is equal to stiffness into displacement, right? Equals to 0, right? Because the joints are in equilibrium, that's why you got 0 here. So for the actions, you need action restrained plus action unit into displacement. Okay, so you need to find this one from here and substitute for here. So from first step, the primary structure, we found this one and this one, right? Now we are okay, and we need to find these from the redundant steps, right? So we are going to do that now. right? So sorry, my I think this is getting erased. I don't know why. So did you remember the values I got? F as WL over 8. This is W, uh, this is negative. WL over 8 positive. This is WL over 12. Action restrained. I got how much? W. So these all are capital W, right? 0, 0, 0, 0, and then right. Okay, so now our step is done, right? So I can go with the redundant step. Here I'm going to go so no loading here. So everything is fixed by still the primary structure without loading, right? So you are going to apply. So you make the kinematic indeterminacy at each 3 redundant 0. So now I'm going to apply that. So I make the bending moment 0, how the rotation was 0. So I'm going to give that rotation. So here I'm going to give a unit rotation, right? So it's the unit rotation. Theta is 1, okay? Not the bending moment. Because this is a displacement we are giving, okay? From that displacement, I need to know which force is generating from the appendix. If you apply one theta here, theta is equal to 1 here, so generated moment is 4 EI over L near far and 2 EI over L, right? So the point is, so you are basically taking the force and the displacement relationship. So this displacement is actually 1. So that means force is equals to stiffness. That's why you use the stiffness coefficient instead of forces, right? So basically stiffness is a force which occurs for a unit displacement, right? So you can take the force, actually the stiffness coefficient at these 3. So S1, 1. So that means the redundant force force induced at 1 due to the redundant displacement at unit displacement at the first redundant, right? So that's going to be, we saw earlier, 4 EI over L. That's clockwise, right? This is also clockwise. And then S21. That's going to be 2 EI over L. Then S31. It's going to be 0. Nothing happens to this beam, right? So this is the total bending moment at this joint, right? Just remember. So the actions. Action unit at, let's call this 1, 2, 3, 4. So here you have 5 and 6 and 7 here, right? I forgot to draw that. Oh my God. So now it's okay. So, but nothing happens to that, right? So the action at first coordinate, second, third, fourth, fifth, sixth, seventh, right? This is AU to 1. The action at action coordinate 1, action unit at 1 due to the unit displacement at first redundant coordinate, right? 1, action at 3 due to the unit redundant at first coordinate. That's how you read it. Because the unit redundant is acting at the first redundant displacement coordinate, right? We are checking what are the forces acting at each action we have that we need, right? So here 1, it's 2 EI over L clockwise, right? 2, nothing happens. 0, 3, nothing happens. 0, nothing happens. 0, 5, nothing. 6, nothing. 7, nothing, right? That's okay. So then we go to the second, right? Right. So we apply a unit moment at now the second coordinate in the clockwise direction. Unit rotation, right? Unit rotation. Here the rotation is 0. Don't forget this beam is 2 EI. Sorry, the frame member. So this is I1, right? So this is my first coordinate, second coordinate, third coordinate. So my S at 1 due to the redundant at 2 and S at 2 due to the redundant at 2 is at 3 due to redundant at 2. So this is the total moment, don't forget. So this is 4 EI over L, this is 2 EI over L clockwise direction. Just look at here. So I will write this one as well. So this is just 2 EI over L. Here you have 3, right? This is the total bending moment. Don't forget the second coordinate is entire total bending moment. So equilibrium means that joint, right? We are considering that joint. So the theta is, so theta is 1, right? Theta is 1 by we are applying a unit displacement and the force is stiffness, right? So we have 4 EI over L here, 4 EI over L here. Here you have 4, that is already 2 EI. L is 3L over 2. So what happens? it's going to be 16 EI over 3L, right? 16 EI over 3L. L is capital L, okay. So I need to add to this 16 EI 3L plus 4 EI over L plus 4 EI over L. Equals to how much? 40 EI over 3L. Okay. So 8 into 3 means 24, 24 plus 16 is 40 over 3L, right? So the actions. My first action, second action, third, fourth, fifth, sixth, seventh. So actions unit due to the second coordinate. Okay, apply that second coordinate. So my action coordinates are action at 1 first coordinate due to the redundant force at second redundant displacement at second coordinate, second action at 3, action at fourth coordinate, action at fifth, displacement occurring at every time second coordinate, right? We include one displacement at a time. We have 3 displacement, we had 1 earlier, now 2, next 3, right? So AU12 is how much? It's 4 EI over L. AU22 is also 4 EI over L. AU32 is how much? 16 EI over 3L. So these are separately for each member, right? So you can see S22 is overall the joint, right? Joint equilibrium. Here, member, each member, right? So here it's half of this, right? If it is 4 EI over L, this is 2 EI over L. If it is 16 EI over 3L, this is going to be 8 EI over 3L. Because the carryover factor is half, right? So fifth, it's 2 EI over L. Here sixth, nothing happens, 0. Because if you rotate this joint, this joint is not rotated, right? But there will be an induced bending moment at fifth. That's why you got this value, right? So now it's okay, and we go ahead and apply so this is our first coordinate, second and third. We apply a unit displacement unit rotation. Okay. Okay. Right. So S1 due to the unit displacement at third coordinate is 0. Nothing happens here. S2, 3. So if you apply for here would be for EIOL, here would be to EIOL, but the overall joint here 0, here 0. Okay, no moment. So that would be overall also to EIOL. So here it would be 4EI plus 4EI over L, because at this joint 2 members are connected, so each member will be rotated. Both of them are clockwise, so every time we got clockwise moment, that's why everything positive. Because this length are L, okay. This is only 3L over 2. Right. So I can find the actions as well. AU right. So I can write here. This is my first coordinate. This is my second action. This is my third. This is my fourth. This is fifth. This is sixth. This is seventh. So this is at first, second, third, fourth, fifth, sixth, seventh. Due to the load at third coordinate. Right. First coordinate, nothing happens. It's 0, right? Second, 2EI over L. Third, nothing happens. 0. Fourth, nothing happens. 0. Fifth, 4EI over L. Right. Sixth, 4EI over L. Seventh, they are going to be, if it is 4EI over L, this is 2EI over L. Why? If you apply a unit rotation, right here, the near end, it's 4EI over L. The far end, 2EI over L, both in the same direction. Clockwise, clockwise, right? So now all the things are done, right? So I can go ahead and find the matrix. So these are for a unit displacement. I need to multiply everything by here by the MA, right? MA is the action, force there. I need to multiply everything by MA. So this is the overall, right? So you remember for displacement, we took the overall moment at that point. Okay. So, and here everything should be multiplied by, It's the displacement, right? So these are for a sorry, I will remind again. So these are forces per a unit displacement, right? So that means these things should be multiplied by the original displacement, right? So what is the original displacement at A is theta A, right? These things should be multiplied by the original displacement at B. That's theta B, because everything is rotated by theta B, right? It's the same amount, the rigid joint, right? So everything should be multiplied by theta C, right? So when you find that, so you can obtain F is equal to stiffness into displacement. So the displacement will be S inverse into minus F, right? So you need to find S inverse, right? So you need to F minus F is known, right? Here minus F is, you can take WL over 24 out. If you take WL over, so minus F means it's negative, okay? So just for now, I will take WL over 24 out. So remaining will be minus 3 plus 3 minus 2. This is F. So the minus 3 minus F would be W minus O WL over 4 plus 3 minus 3 plus 2. So this is minus F plus 3 minus 3 plus 2, right? So that's done. So we need to find S inverse. So what is S in? What is actually S? So you need to pick up everything. S would be how much? If you take 2EI over 3L out. So this is the first, this is the first column, right? So if you take 2EI over 3L out, so remaining would be 6, 3, and 0. So this is the second column. If you take 2EI over 3L out, 3 is coming to numerator then. So 3, 23. Just multiply by and see if everything is there. So here you take 2EI over 3L out, 0, 3, and here 2L. So it should be symmetric, right? You can see this matrix is symmetric, right? Yeah. So finding inverse is not easy manually, right? So what we are going to do is, so you can take this, there would something be 2L. So you can take that and yes, this is how you do it. This is minus f. Okay, this is minus f. F is and this is the matrix you need, right, to take inverse. Okay, right. So you can take this the other way. So that's going to be WL and U. This is, since this is a constant, you can cross multiply. Is equal to this matrix into B. So this is the S matrix. Now no longer this is the S matrix, right? But this part I would say B, right? This is the B matrix, right? Okay. S equals this time into B, right? So I need to find the B inverse, right? So finding B inverse is easy, right? So we can use a calculator. Oh yes, we can use Excel. It's easy. So B is how much? 6, 3, 0, 3, 20, 3, 12, 12, 3, 0. So B inverse is matrix inverse, this part, Control Shift Enter. This is the B inverse, right? So you need to multiply this matrix by the multiplication of the previous step, right? So multiplication of this would give you, so this is 3, 8. So WL squared over 16 EI. So you need to multiply this by B inverse to get, sorry, there's something again. So this is T, right? Displacement. So this is a constant. You don't need to worry on that. So you can just multiply B inverse by this matrix, right? So 3 minus 3, 2, right? So that is actually something called, it's not the actually F matrix because we have taken W, the common term out, 3 minus 3 plus 2, right? So the multiplication would give you the D matrix, right? It should be multiplied by WL cube over 16 EI, right? So from the D matrix, we have taken this out, and how it is coming? So here, W, this is the constant, right? WL squared over 16 EI. So we just need to multiply this by this to get the complete D matrix. sorry, it's squared. So that is also 3 by 1 matrix. Matrix multiply. This is my first matrix, comma, second matrix, control shift. So this is, so this should be multiplied by, so I can write minus 64, 2.8, 23, 64, 28, 23. Right? So this is our D matrix that's found. Right? So I need to plug it here and find this huge matrix, right? So a restraint is here. So you can take WL or 24 out. So that would be 3, 0, 0, 0, and this is minus 2 plus 2. Right? Keep this in, remember, this is action restrained, right? I'll take it to the Excel, that's easy. Action restrained. When you take WL over 24 out, right, that's going to be 3, 0, 0, 0, 0, and minus 2 plus 2. Right? Displacement matrix. So then action unit matrix. I can take so my action unit will be, so first this is the first column, this is the second column, this is the third column, right? Okay, so I can take I can take 2EI over 3L out, right? So you can check freely. You take 3L out. So the remaining will be 3, 6, 0, 0, 0, 0, 0, 0, 0. Why? This is the first column. So numbers, this is first row, first column, first, second row, first column, third row, first column. So everything 0, right? First column. This is first column, right? except this, everything is 0, right? So the second column, you would get 6, 6, 8, 4, 3, 0, 0. This is the second column, right? Second column. The row number is first, right? First notation is the row number. So if you take third column, if you take 2ei over 3l out, 0. Second one is 3, then 0, 0. Then 6, 6, 3. So this is a square matrix, okay. So yes, now I found everything. Can go back to Excel. So I took 2L, sorry, 2EI over out. So the remaining would be 3, 6, 0, 0, 0, 0, 0, 0, 0. Here 6, 8, 4, 3, 0, 0. 3, 6, 6, 0, 0, 3. So this is my action matrix. So my D matrix is this. I need to multiply this by this, right? So the summation would give you, right? The summation would give you the action matrix. This is the actual matrix, okay? Not this. This is the actual matrix. So I will write down it here. Otherwise it's confusing. This is the D matrix, right? So, right, action would be, you need to multiply these both, right? So you can multiply these two, right? If you multiply these two, you will end up with again 2L or 2WL L over 48 EI, right? So that is again WL over 6 EI, right? 24 EI, okay? Plus, so if you multiply these two, it is again WL over 24 EI, okay? Right, so you need to multiply these two. This is your answer. Right. This is equal to WL over 24 into, because the common term is same, you can just edit. So this is your answer, right? So you just can take WL out and divide everything by 24. This is the coefficient. Okay. So these are your bending moment values. So remember, W is equal to simple W into L, right? So if you just need, you can just write WL squared here. Simple W, capital W is simple WL. Okay. Okay. This is the first action. Second action. Right. Seventh action. So that's done. These bending moments will be the final values, right? So if you just consider first three was at the B joint, right? So if you take the summation, what happens actually? That's zero, right? Why? The B joint is already in equilibrium. If you apply, so you remember fourth one is at the lowest point, fifth and sixth at the same joint, right? So if you add fifth and sixth, so that should be zero. That joint is in equilibrium, right? So we just separately found each value, right, using displacement method. So thank you.